Hi everyone. We've seen in the last video the derivation of the proportion confidence intervals. In this video, I'd like to go through an example, a real-world example, of how proportion confidence intervals can be used. The context of this problem is water quality. And here's the setup. This is a problem that occurred in southwest Montana, which is where I used to live. In southwest Montana, there is a river called the Gallatin River. It flows out of Yellowstone Park. And that's the picture on the left. Flowing into the Gallatin River is a small creek called the Spanish Creek. It's a tributary of the Gallatin. Let me bring up my pen really quick, and here you go. And you can see here the Spanish Creek on this map on the right flows into the Gallatin, and the Gallatin, by the way, flows in that direction. Actually, it flows from south to north. Well, the Spanish Creek is owned by a property called the Flying D Ranch. On the Flying D Ranch, there is a commercial bison operation. Okay, and that's this picture here on the left. Spanish Creek, as you'll see here, is in this drawing. No, we do. I think maybe in yellow will show up. In yellow is, oops, sorry. This is the dangers of live videoing. The Spanish Creek is that little section right there. All right. So it's that little sort of ribbon of trees, and the bison are all around it. So the Flying D Ranch is watered by the Spanish Creek, but the bison are essentially in this area, and what goes into the water from the bison goes out through the Spanish Creek and flows into the Gallatin. The Gallatin flows in that direction, flows to a town called Bozeman, and a lot of ranchers use the water. The town of Bozeman uses the water. It's a primary water source. So there's a lot of questions. Does the bison grazing operation on the Flying D, which is the ranch, does it lower the quality of the water in the Spanish Creek and ultimately the Gallatin River? So we're going to see how can we assess water quality using statistics. There's a number of ways to assess water quality. One way is called chemical analysis. You get samples of water and you examine the chemical properties, pH, dissolved oxygen, fecal coliform. But the problem with that, and it can be problematic on a river, is that rivers are flowing. So even if you, oh, there you go. I'm going to change the color of my pen. All right, so even if you take a sample of water and it's clean, it doesn't mean it was always clean, because the pollution will continue to flow downstream. So another way that biologists will assess water quality is they use something called biological analysis. Okay, so biological analysis examines the ability of the water to support life. And one of the primary ways to do that is through macroinvertebrates, or bugs. Bugs, unlike fish, do not spawn. They do not swim up and down the river as much. So they're easier to assess. You can examine a sample of bugs in a particular area. And bugs, for this purposes, are categorized into two, and I'm going to emphasize this, qualitative categories. Pollution sensitive, which means that if there's pollution in the water, those bugs tend to be affected and they'll die off. Or pollution tolerant. Okay, and pollution tolerant bugs are bugs that can withstand some pollution. So in general, and here is the key, right here, the cleaner the water, the higher proportion of pollution sensitive macroinvertebrates or bugs, and those are called healthy indicators. On the picture on the right, you see two of them. That this is part of my research. Here is a little bug. It doesn't look like much, but its common name is a scud, or a freshwater shrimp. That is a pollution tolerant species, meaning that It can withstand a lot of pollution. If the water is polluted, those things will continue to live. This is called the one on the right is called a stonefly nymph. And those are very sensitive to pollution. If there's a lot of pollution in the water, then the nymphs, the stonefly nymphs, tend to die off. So what we did, so here's the flying D, and we divide. You can divide the river. Remember what we're interested in is let me go back to black, sorry. What we're interested in is the water flows into the Spanish Creek from the Bison area. And upstream, the water comes out of Yellowstone Park. It's quite clean. Here is the potential point source of pollution where the Spanish Creek flows into the Gallatin. And what we want to do, or what we did, was we assessed the quality of the life downstream. And here's a picture of individuals. They take these seine nets and they sort of kick the rocks up and the bugs float in, and then they pick the bugs up and sort them, then put them back in the river. So here's some data. So now we'll get into the data. A question you might be asking, why is this statistical? Can we possibly collect all of the bugs downstream of the Spanish Creek? The answer is no. So what you collect, and that's what's happening here in this photo, is you collect a random sample of bugs, of macroinvertebrates. So suppose that upstream, in which the water is known to be healthy, the proportion of healthy indicators is 40%, or 0.4. Remember, for a proportion, you use the decimals. And also remember, the higher that proportion, the healthier the stream. Downstream, we took a random sample of bugs, and here in the picture with our waders, and there are 168 bugs in this net. Of those bugs, 62 of them were healthy indicators. Now you might notice that gives you 62 out of 168 gives you the sample proportion of healthy indicators. P hat, remember, is the sample proportion. That's the symbol, and that equals 62 out of 168. Okay, based upon these data, remember we want to estimate and see if the stream is healthy. So we're going to estimate with 95% confidence the proportion of healthy indicators that live downstream of the Spanish Creek. And then ultimately we're going to compare that to our baseline, which is 40%. So here's the data. So we're trying to estimate the proportion of healthy indicators downstream in the Spanish Creek. And as you do for all confidence intervals and hypothesis tests, here is, let me go to the pen. There you go. Let me go to the pen again. And here is the formula. Always give me the formula for the confidence interval off of your formula sheet. It declares to me what you're doing. This is a confidence interval for a proportion. Why do you use proportions in this case? Because the bugs are placed into two categories: pollution tolerant or pollution sensitive. All right, so those are not ordered. They're just two categories. So this is qualitative categorical or qualitative nominal data, and that's what proportion statistics are for. So in this expression for the confidence interval for the proportion, P hat, we already said, is 62 over 168, which is 0.369. Remember to use the decimals. N is the sample size, which is 168. Z sub C, or the Z critical value, is the normal critical value associated with a 95% confidence, because we already said we want to use 95% confidence. And then so using these data, then the P hat plus or minus Z sub C over the square root of the P hat, 1 minus P hat over N, 0.369 plus or minus 1.96. Remember, this is a multiplication in there, the square root. Do this multiplication first. Take the square root, and when you put that all in your calculator, you should get 0.269 to 0.442. So that's the numbers. Those are the calculations that I'd like to see. And then you have the interpretation. So we are 95% confident that the proportion of macroinvertebrates downstream of the Spanish Creek that are healthy indicators or pollution-sensitive species is between 0.296, or 29.6%, and 0.442, or 44.2%. Now let's go back to the problem itself. Remember that upstream in the clean, the portion of the river that was known to be clean, we had 40% of the bugs upstream were known to be healthy indicators. Based upon the sample that we collected, we can conclude with 95% confidence that between 29.6 and 44.2% of the bugs downstream are healthy indicators. Now, can we conclude based on this data that the river is more polluted downstream? Well, remember, 40% upstream are healthy indicators. We're pretty certain that between 29.6 and 44.2% downstream are healthy indicators. Notice that 40% falls right in the middle of these numbers. So can you conclude that the proportion of healthy indicators is lower downstream? You actually can't in this case. So since that 40% falls within our confidence interval, we cannot conclude that there's a lower proportion of healthy indicators, or that the water downstream of the Spanish Creek is more polluted than the water upstream. The last step in a confidence interval problem, let's examine the validity. We're 95% for 95% confidence. We're given the sample as 106. We're given a random sample of 168 insects was selected. Remember, this is the validity for a sample proportion interval. It's slightly different than a proportion test, as we'll see next week. N times p hat is 168. N is the sample size. P hat is the sample proportion. 0.369. That's 61.99. That is bigger than 10. N times, excuse me, I have a mistake there, so I better correct that. This should be N times 1 minus p hat. That's the third condition, which is 0.68 times 1 minus 0.369. When you do that multiplication, it's 106.1. Random sample. N p hat is bigger than 10. N times 1 minus p hat is bigger than 10. Because all three conditions are met, the confidence interval procedure is valid, essentially, which means that we have good data, we can trust our results.